Let's do x squared. Because that's the one we started off with when we were doing type 1, right? Last class. I started with this example, 1 to infinity of 1 over x squared dx, right? Go in your notes. We found out that this converges. Right? Geometrically, what we did is we said, hey, look at the area from 1 forever and tell me whether or not that's a finite or an infinite area. And we said it converges, right? So that's finite, right? That's what we did last time. Now what I want you to do is not go from 1 to infinity. I want you to go from 0 to 1. That means now I want you to look at this area. See, we have a vertical asymptote here, don't we? If you try and plug 0 into this function, you get division by 0, right? So how do we handle this? Well, here's what I do, all right? You have to see it, right? There's nothing else in this problem that tells you, there's nothing here that tells you that you have a problem other than you identifying it. You have to see that this 0 can't be plugged in, right? You have to see that. So once I know it's a type 2, the standard approach that I like to use is this. I like to draw a number line. I like to put the interval I'm integrating over, 0 to 1. Okay? That's where I'm going, from 0 to 1. And I like to circle where I have a problem. I have a problem at 0, right? Circle it, box it, I'll box it. I have a problem here, don't I? I cannot plug 0 in. What I can do, however, is I can approach 0. I can get closer to 0. And so, since the interval goes from 0 to 1, I need to approach 0 from the right-hand side. So what I'm going to do is, just like I did before, I'm going to replace the 0 with the variable, and I'm going to take a limit, and I'm going to approach that value of 0 with that variable. You know, we did this with infinity, right? Same thing. I'm going to take a limit. I'm going to let t approach what? 0, but from which side? The right. So I need to do a right-handed limit, cal 1, right? We come in from the right of 0, so I put a little plus to the top right of 0. And what I'm doing is I'm replacing the lower limit of integration with t, the upper limit of integration with 1 over x squared dx. Does that seem pretty intuitive? Like we're following kind of what we did with the infinity? The exception being that we're looking at this interval, figuring out where the problem is and which side we're coming in from. Yeah? Now we still need the antiderivative, don't we? We still need the well, we've done that antiderivative several times now, right? So I'm going to do it again. I'm not going to do it again. I'm going to put it in here. So this will be equal to limit t goes to 0 from the right. Okay, the antiderivative of that is -1 over x. I'm evaluating that from t to 1, right? Like that. Make sense? Antiderivative 1 over x squared is -1 over x. We're evaluating from t to 1, and we're taking the limit. This becomes limit t goes to 0 from the right. Okay, fundamental theorem of calculus. Right, so plug in 1 first, plug in t. What do you think? Where does that go? Let t go to 0 from the right.
So it would cause the top to go to infinity.
That's right. You have a fixed number on top, right? Your numerator here is fixed on top. And not only is it fixed, it's a negative number, right? So on top you have a fixed negative number. And on the bottom, you're headed to 0, aren't you? But you're to the right of 0. So do you all agree that these are always little positive numbers? So if you take a fixed number and you start dividing it by small positive numbers, sorry, a fixed negative number, you start dividing it by very small positive numbers, your answer should be huge negative numbers, right? So this goes to negative infinity. So here's what we have. This is negative 1 minus, and then this goes to negative infinity. But that's the same as negative 1 plus infinity, which is infinite, so it diverges. So this is infinite. Diverges. Which is kind of weird when you think about it, because what we just said is that if you take that 1 over x squared function and you look at the area from 1 over here, that's finite, right? But if you take the area on the other side between 0 and 1, it's infinite. That's the way it is, okay? Questions? Are you all liking this more than all the techniques of integration, or how do you all feel about this? Or is it the, eh?
So they wanted us to learn this before learning all the other.
They wanting to learn all of this before what?
Remember these were examples we had.
They wanted us to learn how to do this before we learned all of the techniques.
Oh, well, this is chapter 6, section 6.
Well, I know, but I'm saying the way it was set up.
Well, okay, so remember we learned all the techniques of integration, right? And I said ignore the numbers. And then I said, hey, those numbers, here's what they mean. We jumped back to chapter 5 for us to talk about that. Now we've jumped back to 6.6, so we are past the techniques of integration again. That make sense? So this is assuming we've learned all this stuff. Integration by parts, trig sub, everything's... That's where the improper integrals are. The definite integrals, that's chapter 5. Initially, you may just be like, okay, look, I'm going to have to find the antiderivative of this, and just you go grind it out, right? But there's a problem. Do y'all see where there's a problem? At 4. You have a problem at 4, don't you? 4 squared minus 4 times 4, that's 16 minus 16, that's 0. It's division by 0. That 4 is a problem. So I would have to know that. One way I could figure that out is to take the denominator and factor it. And I have 2 solutions, right? There are 2 places that would cause a problem with that function, right? And one of them happens to be on my interval. So this is an improper integral of type 2 because my integrand becomes infinite at 4. I have a vertical asymptote there. Make sense? Good thing it didn't go from 0 to 4. If it went from 0 to 4, you'd have 2 problems. You'd have a problem at 0 and at 4. But here we just have a problem at 4. So, yes. And sometimes your problem is somewhere in between. So like if I went from 1 to 8, you have a problem at 4, right? So you would have to, I'm going to do one of these, but you would have to go from, if this went from 1 to 8, what you would have to do is this. You would have to break it into 2 integrals. One goes from 1 to 4, and the other one goes from 4 to 8. And then you have to do 2 separate limits. We'll get there. Okay, so I have a problem at 4, right? So I'm going to draw my number line, 1 to 4. Here's my problem. It's at 4. And so I'm going to approach 4 from the left, right? That's what the limit is that I'm going to set up. limit t goes to 4 from the left, so a little negative sign on that 4. And then integral 1 to t, 1 over x squared minus 4x dx. Anyone have any idea what I'm about to do? I need to find the antiderivative, right? So I'm going to set that problem up over here. And when I look at that problem, I go, shoot, partial fractions. Right? I have to recognize that this is going to, the only way I can go after this is if I factor it. Right? This is a quadratic on the bottom, constant on top, quadratic on the bottom, but it's factorable. So when I factor the bottom, I can do partial fraction decomposition. So over here, I do my partial fractions. These are both distinct linear factors. So I'm going to put a over x and b over x minus 4. Kill off the fractions. So get rid of the, multiply both sides by this, right? Am I going too fast? You following? You could do the short method here, or you could do the long method. I'm going to do the long method because I just don't care. All right, so ax, it's not that bad, 4a plus bx. All right, just distribute that out. I'm going to collect my x's together, so I have an a plus a b together with the x, and then a minus 4a here. So I put those two together, factored out an x, put that right here. And I don't have an x term on this side, right? I have no x's, which means that a plus b has to be 0, right? And then negative 4a has to be this constant. Oh. So I have that negative 4a had to be 1. That means a is negative 1/4. And once I know what a is, I know that a plus b has to be 0. But if a is negative 1/4, that means b has to be positive 1/4. We good? So now this becomes the integral of a over, what's a? A is, so negative 1/4 over x, and then plus b, which is positive 1/4 over x minus 4 dx, like that. Any questions? Both of those are logs, right? Natural logs when you take the antiderivatives. So I'm ready for an answer here. I've got the negative 1/4 out front. That constant comes for the ride. Antiderivative of x is natural log absolute value of x. Plus this 1/4 comes out, natural log of x minus 4. Plus some constant, there's my antiderivative. Back to this. Limit t goes to 4 from the left. Okay, my antiderivative I just got was negative 1/4 natural log of absolute value of x plus 1/4 natural log of x minus 4. Evaluating that from 1 to t. How are y'all doing? we're going to have to plug t into this, right? And then we're going to have to plug 1 into this and subtract, right? Okay, so I'm going to see, can I do that right now? I'm going to just try and do it all in one line here. Approaching from the left. Okay, first I plug in t. I get negative 1/4 natural log t plus 1/4 natural log of t minus 4, absolute value. Okay, that minus now negative 1/4 natural log absolute value 1 plus 1/4 natural log of absolute value of 1 minus 4. There we go, like that. So that's me plugging t in for everything, and then subtracting what I get when I plug in 1 for everything. Do y'all see how important that absolute value is now? Right here? 1 minus 4, negative 3. Absolute value makes it positive 3. Then you can plug it into the log. Natural log of 1 is 0, right? So this is all good here, right? We just got to figure out what's happening here. See if we can do this without any more work. If I take 4, right, and plug it in here, natural log of 4 is a number. Yes? No problems there? Okay, so that's okay. What about when I take this 4 and I plug it in right here? You get 4 minus 4. And that would give you 0, wouldn't it? And what is natural log of 0? It's undefined, right? But we're approaching 0. Look, we're approaching 0, right? Because this is getting closer to 4, which means this in here is getting closer to 0. And since we're taking the absolute value, it's always a positive number. So what does the natural log function look like as you approach 0? Where is it headed? It heads to the natural log function as you approach 0, right? Here, it goes to negative infinity, which means this thing goes to negative infinity. And once you got that, you're done, because that goes to a number, that goes to negative infinity, that's all numbers, so you have what here? Divergence. Or divergent, or divergence, diverges, however you want to say it.
When we're working out these diverging and converging problems, if we stop halfway through our work and we circle that it's divergent and convergent, because we've done all of that work, we don't have to have the actual complete answer for the moment in order to know, and we need to stop when we know.
You need to stop when you, like here, you would need this work, okay? You couldn't just like, what I haven't read here, you couldn't not have that and just say that that's divergent. Like you have to show me why.
That's what I'm saying with that right there, just as it is.
Yeah, I mean, I would do one more thing. I'd say this is a number, okay? That's a number. That's a number, right? So basically you have, a number minus infinity minus a number plus a number. This is going to be minus infinity. Yeah? The problem is this. Look, here's the problem. What if this was minus infinity, right? And this was plus infinity? Minus infinity plus infinity? You know what I'm saying? So you need to make sure you've analyzed everything. Do you want to do one more? Or? Yeah, let's do it. That one right there. So one of the things that trips students up, and I've just mentioned this a moment ago, is that they get so like gung-ho about being able to find the antiderivative of something that they completely forget that you need to be like on the lookout for improper integrals. So they're like, oh, I just need to go find the antiderivative and then plug in the two endpoints and then I'll be done. That can get you into some pretty big trouble. Let me see, I'm trying to think if I can just give you a real quick example before I do that one. Yeah, let me just do this real quick. So what if I had this? Integral 1 to 5 of 1 over x minus 2. Yeah, let's just do that. dx. Here's a major mistake, all right? Student looks at that, they go, oh, I know the antiderivative of that. It's natural log absolute value, x minus 2. Do you all agree that's it, antiderivative? Yeah? Evaluate that from 1 to 5, okay? Plug in 5 first. You get natural log of 5 minus 2. Okay, take that, subtract from that. Now plug in 1, natural log absolute value 1 minus 2. Right? This is natural log of 3 minus natural log of 1. So your answer is natural log of 3, because natural log of 1 is 0. Do y'all see what I did there? Yeah. This is all wrong. Why is this wrong? Because I have a problem at 2. You can't plug 2 in here. And 2 is in between 1 and 5. So you can't do this. This is completely wrong. This is an example right here, similar to this one. Right? You could go try and find the antiderivative of this. Go do it. But you have to realize you have a problem where? At 4, right? 4 can't be plugged in here. So what you're going to do is this. You're going to break this integral up. You're going to go 3 to 4 of this. Then you're going to go from 4 to 5 of the same thing. And you're going to have to do a limit on this one because you have a problem at 4, right? You have a problem here, and you have a problem here. So on this one, I'm integrating from 3 to 4, which means I need to approach 4 from the left. And on this one, I'm integrating from 4 to 5, and I have a problem at 4, so I need to approach 4 from the right. You'll see I'm going to have a limit, 2 limits, 1 for each of these. And then we're going to need to set up, like actually do the antiderivative. That's another step. But let me just write down what I'm going to have in terms of limits. Limit, let's use t again. T, where's t going to go? On the first one, it's going to be, I'm approaching what though? 4 from the left, and then it's going to be 3 to t, right at the top. And then whatever this is. Then plus, I'm going to put it right here so I don't hit this thing. Another limit, this one I'm going to use r goes to 4. This time I'm approaching 4 from the right. And I'm replacing the lower limit with 4. The top one's going to be 5, and then I still need the antiderivative. Y'all see how this is going to work out? It's going to split up into two integrals, 2 limits, and then I got to go do all that. All right? That's what you would have had to have done here as well. You go from 1 to 2, then 2 to 3. Or sorry, 1 to 2, then 2 to 5 is what you would do here. Split it up into 2 and do limits. Let's stop. I think, could you handle this antiderivative? How would you do that? Anyone have an idea of how to do this antiderivative? Basic U sub. Let U be x minus 4. du is dx. Rewrite the problem. What does the bottom of this integral become? The bottom. Cube root of u. Cube root. Dx is du. And then what's x? You have to solve for this, so u plus 4 or 4 plus u? And the whole point of that is now you can split it into two, right? You can do u over this, 4 over this, and just do power rule. Okay, so this check, I'm just going to say that can be taken the rest of the way. Find the antiderivative, then come back over here, plug it in, then you're going to have to do your limits and stuff, right? I want to save some time to answer any questions you might have about the exam. I sent out those tests last week. Reviews or anything? No? How many problems were on those tests? Usually about 5 or 6 problems, right? So you'll have 100 minutes. So 5 or 6 problems. Some of them are going to be longer than others, right? But from doing the reviews or looking at those, you can tell what I'm testing you on, right? It's problem recognition, looking at it, knowing what to do, right? Trig sub. Were there any trig integrals where I just gave you like sine, cosine, tangent just by itself on those tests? Did you see anything like that? No, because trig sub is going to require you do that anyway, right? Partial fractions. Those are like the 2 main topics, right? Trig sub, partial fractions, and then there may be some integration by parts in there when I get to the definite integrals and impropers. We want to look at any of them, or did I send out answers to anything or no? No. I didn't, right? Well, didn't I send you like 4 reviews or something?
You sent us 3 old tests.
3? Let me see what I sent you.
I think the review had the answers, not you.
Let me see. Sent to you all. Exam 2 review. Let's take a look at that one real quick. Just want to see which one it was. So this is not a bad review here. Let me see if I have some answers to that. Just making sure it's the right one. Yeah. I can send you this one. These are the answers to the review one. The one that said review on it, I can send you all that. The others I won't, but on that review though, the thing I like about that first problem, it's trig sub, right? But you have to factor a 9 out first. You can't do trig sub until that number in front of 9, or in front of x squared is a 1. This one is, I think, a straightforward trig sub. For what, tan? Okay, this one, oh, those are like my favorite problems, where you have a linear on top and an irreducible quadratic on the bottom. And I showed you my way, and I showed you the way that the book does it. So, and then this one requires partial fraction decomposition. You're going to get irreducible quadratics, so you're going to wind up with, like, you know, ax squared or bx plus c, things like that. Long division first, number 5, long division first. And you have to factor the denominator. Number 6 would not be on there, I don't think. Hold on. That's not improper, is it? It doesn't go to infinity. So this number 6 is just a definite integral. But to do it, you have to do integration by parts. So I would say this is a good review, but it's missing a type 1, right? It's missing a type 1. So what about the others? Let's see what this one looked like. Let's look at this one. So what's the big difference here on this test? Basic, straightforward, trig sub. Basic trig sub, it's just tricky because of the cubed here. You just got to just be careful on that one. There it is again. Irreducible quadratic on the bottom, linear expression on top. You're guaranteed to get one of those, guaranteed, right? This is another partial fractions with long division first, right? Here we go. Here is an improper type 1 with partial fractions. So that would be similar to the problem I did just before this one. Right, we had to do partial fractions first? Please tell me, yeah, there was only 5 questions. That's pretty involved there. What did I do, full 19? Straightforward? See, but when I say straightforward, I mean the trig sub is straightforward, right? After that, it could be a bunch of stuff that could happen, right? You could have sines and cosines, or you could have tangents and secants, and then that might be where it's an even power, so you have to do power reducing formula, or it could be odd, where you have to peel off a sine or a cosine, right? There's all these different scenarios, but there's nothing tricky about it in terms of what the trig sub is. Where the hell's the next one? Okay, partial fractions. Long division first. Long division again. Oh, and that's a definite integral as well. So they had to do it, but then they also had to evaluate it. Improper. Hey, we did that problem today, but we went from negative infinity to infinity. I had them go from negative infinity to 2. So this answer is actually finite. That does converge.
You said there would only be type 1 problems, though, right?
That's a type 1.
Yeah.
But this is a type 1 that had L'Hopital. I guess I said no L'Hopital, didn't I?
Yeah.
I guess I did. Sometimes I don't know why I say the things I say. But you're going to have it at some point. You'll have it, right? So next exam. All right, here we go. This won't be on the test. This isn't type 2 improper integral. Does everyone see that that's type 2? You have a problem at 1, right? Okay, so that won't be on the test. Was there another one? Ooh, type 1. That's fair game right there. It looks worse than it is. It's 2 irreducible quadratics side by side. So you have to do like ax plus b over this, cx plus d over that. Probably use a calculator to solve the system of equations. And then once you get it broken down, x squared plus 1, x squared plus 4, that'll be like arctan. There'll be arctans in there. So you can mess with that. How you feeling?
So do you know the type 2, if there's a problem, like on the numbers? That's how you know that it's type 2?
For type 2, what you're doing is you're looking at the function and seeing if there's anywhere that it's undefined, and then seeing if those